In this video, we're going to talk about another important area of calculus, which is finding the area under a curve. So we're going to start by approximating the area, and then later we'll see how it relates to calculus and integrals in particular. So we have multiple formulas to determine area for geometric shapes, which are obviously curves, so like triangles, rectangles, circles, etc. But here we want to think about just a general curve. So we're going to approximate. So let's start with one that we know how to do. Okay, so here we can actually determine the exact area. So the area between the curve f of x is square root of 4 minus x squared, the x-axis, and the interval from 0 to 2 for x. Okay, so you might not recognize this one right away, but this is actually, so if I write it as a y instead of f of x, it looks like this. And then if I square both sides and move the x squared over, I'm going to have x squared plus y squared equals 4. This is the equation of a circle. Okay, so then the f of x here is the top half of the circle. Okay, so this is the top half of a circle centered at 0, 0 with radius of 2, so square root of 4. You can draw a picture of this. So what it's going to look like is something like that. Okay, where this point is negative 2, 0, this point is 2, 0, and this point is 0, 2. So it's the top half of the circle. So the area that we want is the area underneath and between the top half and the x-axis. So that's the area we're trying to find. So here it's half of a circle. Oh, sorry, I lied. Between 0 and 2. So it's actually only the first quadrant area. Okay, so this is actually the area that we want. So it's going to be a quarter of the circle. Okay, so the area here is 1/4 the area of the circle. Okay, which is going to be 1/4 pi, and then our radius is 2, so pi r squared. So this is actually just pi. So the exact area is pi. So now we're going to try and approximate this area using rectangles. And this is actually one way that they did approximate pi back in the day. So here we're going to use 2 rectangles. Okay, so I'm going to draw the shape again, but only on the part that we care about. Okay, so it's going to look something like that. Okay, so we're going to use 2 rectangles, and we're going to use equal sized rectangles. So that means, because this is at 2, we're going to split at 1, so their width is the same. Okay, so I'm going to split, and then the left endpoint, okay, what that means is that we're going to use the y value of the left side, okay, as the height of our rectangle. Okay, so in a picture form, what that's going to look like is we're going to use this y value as the height for that rectangle. Oh, I lied. The left, that's the right endpoint. So for the left endpoint, we're going to use this, the left side height, to make our height of our rectangle, and then similarly on this side as well. Okay, so I have 2 rectangles here. So this one and that one. So we want to approximate the area by computing the area of these rectangles. Okay, so the area is going to be approximately the area of, I'm just going to call it rectangle 1, plus the area of rectangle 2. So the area is going to be the length times the width. Okay, so the width here for both of them is 1. the height of the first one is going to be f of 0 because it's the y value when x is 0. And the height of the second one is going to be f of 1. Okay, so then we're going to do width times height. So this is going to be 1 times f of 0 plus 1 times f of 1. And we know the equation for f. So this is, the y value here is 2. Maybe I should use the equation. So it's going to be the square root of 4 minus 0 squared. And then over here it's 1 times the square root 4 minus 1 squared. So this is going to be 2 plus the root of 3. And if you compute that, you get 3.7321. Okay, now this number is bigger than pi. Okay, so that means that we have an overestimate, which makes sense given our picture, because the rectangle heights are higher than the circle boundary. So we get some extra area. So it makes sense that we got an approximation that is bigger. Okay, now we could use instead the right endpoints. Okay, so again, I'm going to do this a few times to show you all the ways that we can do it. Okay, so here's 2. We're again going to split at 1 because we're still using 2 rectangles. Okay, but now we're using the right endpoint to make the rectangles. So this one actually, we end up, the height of one rectangle is 0 because that's the y value on the right hand side. Okay, so here we would say the area, again, is approximately the area of rectangle 1 plus the area of rectangle 2, which happens to be 0. So they again have width 1, okay, but this one has height f of 1, which we already found. So just to make things simpler, this is going to be 1 times root 3 plus 1 times 0. So our approximation is root 3, which is approximately 1.7321, okay, less than pi, which again makes sense that this one is an underestimate because we have all of this area that we missed. Okay, now let's try it again. This time though, we're going to use a midpoint for our height. Okay, so I'll draw my shape again. They're getting worse, I think. So we're using 2 rectangles, so we split it into 2. Okay, but then I'm going to use 1/2 and 1.5 as my height. So that's the midpoint in each of these intervals. So I use my height here, and I use that for my height. And notice now it's hard to tell whether we're going to have an underestimate or an overestimate. Okay, so the height here is going to be f of 1/2. And the height of this one is f of 3/2, or 1.5. Okay, so then the area, again, is approximately the width times the height plus the width times the height. So I'm just going to go right to the answer here. The height is for 1/2 is 15 over 4, and the height for 3/2 is 7 over 4. So these are in the square roots. So this is approximately 3.2594. Okay, so it's still a bit bigger than pi, it turns out, but closer. Okay, so this is a better approximation. Okay, now what about if we use 4, so more rectangles? Okay, so we could use 4. I'm just going to use the left endpoint because it's a bit easier, and it turns out that it doesn't actually matter. Okay, so because we're going to split into 4 rectangles, I'm going to split this into 4 pieces. Okay, so then I'm going to get 4 rectangles. I'm using the left endpoint for each. Oops. Okay, those are terrible rectangles. So I add up all of these areas. So now I have 4 things to add up. And we can see that we're probably going to get an overestimate. Okay, so it's 1/2 times, so now the length is less. So it's not 1 anymore, or sorry, the width. Each of these is 1/2, right? Because we split it into 4. So it's 2, the width 2 divided into 4 pieces. So it's 1/2 times f of 0 plus 1/2 times f of 1/2 plus 1/2 times f of 1 plus 1/2 f of 3 over 2. And we already computed all of these, so I'm just going to plug them in. So 1/2 was square root of 15 over 4. F of 1 was root 3. And f of 3/2 was square root 7 over 4. Okay, now if we compute this, it's 3.4957. Still bigger than pi, okay, but better if we compare to our first one. It's closer to pi than when we use the left endpoint and only 2. Okay, so better than 2 rectangles with the left endpoint. Okay, and it turns out that the more rectangles we use, the better the approximation. Okay, so if we use n rectangles, the bigger n is, the better the approximation. Okay, now often the midpoint is sort of the best one, but what we're going to be doing is letting the number of rectangles go to infinity, and if you do that, it doesn't actually matter which endpoint you use, and the left endpoint is usually the easiest one to work with. So if we use rectangles of equal width, each rectangle is going to have width we call delta x. Okay, and it's going to be, for this example, it's going to be 2 divided into n bits. Okay, so y2, this is the width of the interval from 0 to 2, right? That's the one we were working on. So it's that width divided into n parts. Now, if we take the sum of the areas of these n rectangles and we so the more and more rectangles we do, the better the approximation is going to be. So if we let the number of rectangles go to infinity, and we think of the limit as that happens, what's going to happen if we add up the areas, we're actually going to get the actual area. Okay, so there's going to approach the actual area. So in our example, this would equal pi, right? Because that was our actual area. Oh, and that's what I wrote here. So pi was actually approximated using a method similar to this. Okay, we can generalize this to any curve too. So suppose here's our curve, and we want the area, so let me just highlight it here. So the area under the curve between the lines x equals a and x equals b and above the x-axis. So we want to know how much area is in here. So what we're going to do is approximate it using rectangles. So I'm just going to draw some rectangles, and it doesn't actually matter which endpoint you use. So I could use even the left endpoint for some, maybe the right endpoint for some, okay, maybe the midpoint for others. Okay, it doesn't actually matter. Obviously you can make it better by choosing a good endpoint or a good one to use. Okay, but it doesn't actually matter. So I would compute the areas of all of these rectangles. And that would be my approximation for the yellow area. Now, obviously, if you use the same endpoint or the same x value in each interval to approximate, then it's easier to generalize. Okay, but if we do this, each rectangle is going to have width, so it's going to be this width, which happens to be b minus a, okay, divided into n parts. So each rectangle is going to have width, we call it delta x, it's going to be b minus a over n. Okay, it's the length of the interval from A to B. Okay, and this is the number of pieces, so the number of rectangles you're going to break into. That's if you use equal width rectangles, which we're going to do. But again, you don't have to. Okay, then what we're going to do, we select an arbitrary x value in each interval. Okay, so like I said, this is just one x value in each rectangle. It's easiest to generalize if you pick the same x value, so like the left endpoint of each interval or the right endpoint of each interval. But it doesn't actually matter. Then we're going to compute the area for each rectangle. So the area of rectangle 1 would be delta x, so the width, times the y value of the x point that we picked. Okay, so this is the width, and this would be the height, because we chose the y value at x equals x1. Okay, so the area of rectangle 2 is going to be delta x times f of x2, etc. So the last rectangle is going to be delta x times f of xn. So if we add all these up, we get something that looks like this. So I get a sum with n terms. Oops. This is hard to work with. Okay. So what we want to do is we want to write this notation a little bit more succinctly. So what we're just going to take a brief sidetrack into some notation. So this is a sum. This is a sigma. It's a capital sigma, so a Greek letter. But in math, it means the summation. Okay, so this is a sum. Let me just write that. Okay, so this is a summation symbol. Okay, and then the bottom bit means that we start at k equals 1, and the top bit means that we end at k equals n. And then the thing that's inside the sum, this is our formula for the kth term. Okay, so what this would look like if we were to write it out, it would be a1, so that's the k equals 1 term, plus a2 is the k equals 2 term, plus a3, and then so on until we get to an, which would be our last term. Okay, so that's what it means. Okay, so let's just do some examples. So if I wanted the summation from k equals 1 to 4 of k, so this is our formula. When k equals 1, I just get the number 1. Okay, so this is the k equals 1 term. And then I want to add to that k equals 2. Okay, when k is 2, I just get 2. And I end up summing the first 4 integers. Okay, so this sum would equal 10. Okay, etc. Let's use a little bit more complicated formula here. So here I want to sum up squares. So I start at k equals -1 and I go to k equals 3. So my first term is going to look like -1 squared. So this is the k equals -1 term. And then I want to add to that the 0 term. So that's going to be 0 squared. So that's k equals 0. And I'd have to do that until I get to 3. So I'm going to have 1 squared plus 2 squared plus 3 squared. So I end up with 1 plus 0 plus 1 plus 4 plus 9. So I think I get 15 here. Okay, one more. So here I start at k equals 0. My formula looks like 2k plus 1. So when k equals 0, I'm going to have 2 times 0 plus 1. And then I'm going to add, when k equals 1, I have 2 times 1 plus 1. And then when k equals 2, I have 2 times 2 plus 1. So let me just write, this is k equals 0, k equals 1, k equals 2. So this is going to be 1 plus this is 3 and plus this is 5. So it's the sum of the first 3 odd numbers. That's going to give me 9. Okay, so that's just a quick introduction into summation notation. You may have seen this before, you may not have. Don't stress about it. We're not going to be using it that much. Basically, I need all of this so that I can talk about the definite integral, which is where we're going after. So, back to the area. So in our previous example, so that we would approximate the area by adding up these the rectangles areas, which look like this. Okay, so now if I notice, each of these terms looks very similar. Okay, the only difference comes in this number here. Okay, which x value I picked. So I could just let the k's be those numbers. So this would be the k equals 1 term. This would be the k equals 2 term. This would be the k equals n term. And each of my terms is like delta x, f of x, k. Right? So that the 1 here matches the 1 here. The 2 here matches the 2 here. That's my k value. So this is the area for the kth rectangle. So that will be my formula for in my summation. So my area is going to be approximately equal to the sum from k equals 1 to n for my n rectangles, the area of the kth rectangle. So the width times the height. Okay, so this part is the width of the rectangle, and this is the height of the rectangle. Now, as the number of rectangles grows, my approximation gets closer to the actual area. And if I actually take the limit as the number of rectangles goes to infinity of this sum, okay, this is going to look very complicated. Okay, if I take the limit of that, my approximation, the number of rectangles goes to infinity, that's what that means, I actually get the actual area. Okay, now we in this class, so this is called a Riemann sum. This is a sort of specific, not as general of a Riemann sum as you could have, but this is called a Riemann sum. We're not going to actually do these in this class, so you're going to be responsible for approximating areas using a given number of rectangles and an endpoint. Okay, so something like this. So I would say use 4 rectangles and the left endpoint and approximate the area. So you're going to be responsible for something like that. But we still need to understand why, as the number of rectangles goes to infinity, that we're getting closer and closer to this area that we want. Because it turns out that these Riemann sums are very important, even though we're not going to compute them in this class. But we're going to define the definite integral using this idea. Okay, so to be this limit of the sum. So that's where we're going. That's why we needed all this. So what I want you to understand or to take from this is just that we can use rectangles to approximate the area. You need to know how to do this using a given number of rectangles. And then we're going to use this idea to talk about the definite integral and how that relates to areas under a curve. Okay, and we're going to be computing these not by evaluating this limit, but instead using the fundamental theorem of calculus or known areas that we already know. Okay, so this is sort of the idea. This is the build up to the definite integral. So hopefully that makes some sense and doesn't scare you too much.